In this problem, we're told that a gas in a piston cylinder assembly undergoes two processes A and B between the same end states. So process A is a pressure-volume relationship, which is given by PV is equal to C. Process B is a constant volume from state 1 till it gets to 2 bar, and then a linear pressure volume to state 2. We're told that we can ignore our potential and kinetic effects, and we would like to sketch this on a PV diagram. We want to evaluate the work of each process A and B in kilojoules and evaluate the heat transfer in kilojoules of each process. We're also given the initial pressure and volume. So our initial pressure is 10 bar, our initial volume is 0.1 meters cubed, and our initial internal energy is 400 kilojoules. Our final pressure is 1 bar, our final volume is 1 meters cubed, and our final internal energy is 200 kilojoules. So let's start by drawing this on a PV diagram. So with our PV diagram, this will be pressure, and we're going to have it in bar, and this will be volume, and we're going to have this in meters cubed. So we start at some high pressure of 10 bar, so right here, and this is our initial state, state 1, and we'll say this is 10 bar. And state 1 then goes down here to 1 bar. So over here is 1 bar. Well, we were told that the pressure-volume relationship is given by PV is equal to C. So it's some polytropic process. It's actually, if we had N right here, N would just be equal to 1. So it's some process, and this is what the process will be. It's not linear, but it has some sort of curve to it, and we're doing this. So this is process A. Okay? Now let's do process B. So process B is a constant volume process from state 1 until it gets to 2 bar. I should probably label what these volumes are. We know what they are. So V1 is 0.1 meters cubed. V2 is 1 meter cubed. So with B, we go a constant volume process until we get to 2 bar. So right here, we get to 2 bar. And then we have a linear process from 2 bar until we get to state 2. So state 2 is right here. And this entire here to here is process B. So this is the PV diagram. Now let's start with process A and figure out the work of process A. So we know it's a polytropic process because it's given by PV is equal to C, and our work is equal to work is the integral from some change in volume, V2 to V1, of the pressure dV. Okay, because it's a polytropic process, PV is equal to C, we can solve for pressure, and we can get pressure, let me do it here, pressure is equal to C over V. So I'm going to substitute that in right here. So I'll get W, work, is still this integral from V2 to V1, but now it's going to be C over V and dV. One other change I can make, because this is a constant, I can just bring it outside the integral. And if I do that, I'm going to get work is equal to this constant C times the integral of V2, V1, 1 over V times dV. So now this is an easy integral to take. We know that it's the natural log. So the work is going to be equal to C times the natural log of V2 minus the natural log of V1, and C is multiplied by both of those. So what is C? Well, we can get C by using this relationship right here. And what we can say is it doesn't matter. We could say P1 V1 is equal to C, or we could say P2 V2 is equal to C. We get the same answer, right? So if we do 10 times 0.1, we get this is 1 bar meter cubed. If we do it the other way, 1 bar times 1 meter cubed, we get this is equal to 1 bar times meters cubed. So it doesn't matter which one we choose. We get the same answer. So all that matters is we do need to pay attention to the units. So we get 1 bar times meters cubed. Okay, right, we can simplify this, and that can be the natural log of V2 over V1. And if we substitute our numbers, we're going to get this is equal to 1 bar times meters cubed times the natural log of V2, which is 1 meters cubed, over 0.1 meters cubed. And now all we need to do is deal with our units, right? We want this in units of kilojoules. Right now we're in some bar meter cubed. These two are going to cancel out, but to do this, first we're going to take care of our bar. So 1 bar is going to be 10 to the 5th newtons over meters squared. And then we're going to get it to kilojoules. We're going to say 1 kilojoule is equal to 10 to the 3rd Newton meters. We can check our work. We can say, okay, so my bar is going to cancel with a bar. This 10 to the 5th is going to become 10 squared because it's going to cancel with 10 to the 3rd. My newtons right here are going to cancel. This meter and this meter squared are going to become a meter cubed. And then that meter cubed is going to cancel with that meter cubed. And all I'm left is with kilojoules. Okay, so that's good. Let's put this in the calculator. So I'll have the natural log of 1 divided by 0.1 and times 100. And we get that this is equal to plus 230.26 kilojoules. I just made it on the screen. Move it over. Okay. So now we figured out what the work was. The work is 230.26 kilojoules. It's positive, so that means our system is doing that work. And we want to evaluate the heat transfer of part A. Well, we don't necessarily have an equation that we can just solve for Q like we could for work, and we can't solve for it directly, but we can use the first law of thermodynamics. That says that the change in my energy is going to be equal to Q minus the work. And so this is going to be the change in energy from 1 to 2. Q of 1 to 2, and we'll annotate this of A, and work 1 to 2, we'll annotate this as A. So this work we already found. This work is right here. Let's break apart our change in energy. Our change in energy is going to be the change in kinetic energy plus the change in potential energy plus the change in our internal energy. is equal to this I'll just denote it Q1 to 2. We know we're talking about process A minus W1 1 to 2. Well, we were told right here that we could ignore potential and kinetic effects. So these go to 0. So all we have is some change in U. So this change in U is going to be U2 minus U1 is equal to Q1 to 2, which is what we're looking for, minus our work from 1 to 2. Okay, let's just put our numbers in. So with our numbers, we get U2, this is 200, and it's in kilojoules, minus 400, again, kilojoules, so we're good with our units, is equal to Q1 to 2, minus this work. So minus 230.26 kilojoules. Everything's already in kilojoules, so our units are good. So now we can do 200 minus 400 minus 2, so that's minus 200, and then we can add in plus 230.26. And we get that this is equal, so Q 1 to 2, I guess of A, is equal to plus 30.26 kilojoules. So that means that this heat is coming into the system. So this is the heat and work for part A. So now let's look at process B. Process B first has this constant volume process. So right here we'll have B. The work of B, we're going to break up into each of these processes. So we'll call this right here, we'll call this B1. And right here, we'll call this B2. So the work of B is equal to the work of B1 plus the work of B2. But what's happening in this work of B1, it's a constant volume. A constant volume means no work is being done because the volume's not changing. So we know that this right here is going to go to 0 because it's constant volume. So now all we have to do is figure out the work from this B2 area. So work of B2, it's linear. If you had watched my previous video, the equation for linear work from two states is going to be the average pressure, so P average, times the change in volume, so V2 minus V1. The average pressure is going to be equal to 2 plus 1 divided by 2. Our change in volume is going to be 1. This is V2, which is 1, minus 0.1, our V1. And we get that this is equal to 3 divided by 2 times 1 minus 0.1. 1.35. And I didn't do this conversion, but I'd still need to do that conversion. So this is bar meters cubed. Then we're going to do 10 to the 5th Newton meters squared over 1 bar times 1 kilojoule over 10 to the 3rd Newton meters. So really we're just multiplying it by 100. And we get this is equal to 135 kilojoules. Okay? And finally, we now just need to find the heat from process B, the heat transfer. So just like process A, we start with our change in energy is equal to Q minus W. Again, we know our change in energy. We can ignore the potential and kinetic effects just like we do right here. So we're going to have, again, this becomes our change in internal energy is equal to Q minus W. So we'll have U2 minus U1 is equal to Q 1, 2, and this really is B, right, for process B, minus W1 to 2, process B. So this doesn't change. It's still 200 minus 400 for our change in internal energy. This is equal to Q1 to 2B minus this 135 kilojoules. So now we can just put that in our calculator. So we'll have minus 200 plus 135. And we get that this is equal to minus 65 kilojoules. So Q 1 to 2 of part B, or process B, is equal to minus 65 kilojoules. So that means our heat transfer is out of the system.